thank you very much for the introduction, and thank you for the invitation. This is a pleasure and a great honor to be here and give this talk. So everything I say today is a joint work with Fang Hao and Yangchang Liu. So the story begins from a conjecture, rather a question that was studied by Kochik, and it's about X, a smooth projective variety over the complex numbers. And since I'll be talking about one-forms, let's make sure they have one-forms. So they are irregular, which means that the space of global holomorphic one-forms is non-zero. Okay, so the question Kochik asked was that the following should be equivalent. So the first criteria is that there exists a holomorphic one-form, so a section of the cotangent bundle, such that it doesn't have any zero. Yeah. So it's an over-vanishing one-form. So since this is a one-form, let me also write it in a differential geometric fashion. So basically this means that if you look at the set of points in X such that it's a one-form, so it acts on the tangent space at the point, then that should be zero. So you look at all these points on X, then this is empty. That's what I mean when I say nowhere vanishing one-form. So the expectation is that this is equivalent to saying that there exists a C infinity fiber bundle structure over the circle, like the real circle. So this is a submersion. So this was studied a long time ago by Tischler, and he had shown for real manifolds. And the result at that time, so 1 implies 2 is classical. And the idea is that, okay, if you have a holomorphic one form that doesn't vanish anywhere, so you have a real one form that doesn't vanish anywhere, so then he constructed the map out of that data. Okay, so then a few years ago, Schreider connected this problem to generic vanishing theory, and he gave a third criteria, which is there exists a one form on X such that for all finite étale covers of X, if you consider the long exact sequence, so let's say the cohomology, I take the kth cohomology for some k, and I look at the higher exterior power of the cotangent bundle, and then I wedge it with omega, right? So it will go to the next exterior power. So this is a long exact. This is a complex, and what he wants is that there exists an omega for which, for any finite étale cover, this complex is exact. So this is equivalent to saying by Hodge decomposition. Yes, sir. Yeah. So X prime, and then I want to wedge with the pullback of the one form. So the one form should come from X. Thank you. Not really, but the cases where it's known, it turned out to be the same form. But yeah, it's not clear. Okay, but so by Hodge decomposition, I can put them together to construct this linear complex, also known as resonant complex. This is expected to be exact. Right? So and then he showed that 2 implies 3. Okay. And then exactly, yes. So actually, yeah, all the criteria I'll give, one will be the strongest. So everything follows from 1. But I think 2 to 3 was more non-trivial. Okay. Okay. So then so we proposed a 4th criteria that has to do with the Albanese morphism. So as you know, the Albanese morphism, I'll denote it by A from X to AX. And a quick reminder that the Albanese variety is basically functions on the space of 1 forms that are path independent. So as you can see that all the 1 forms on X comes from 1 forms on AX. So in many cases, I'll identify 1 forms on X and 1 form on the Albanese. Okay, so you consider this Albanese morphism and then look at our criteria is there does not exist a variety Z containing the abelian variety AX of general type. And in Kramer's talk, we saw that this means the Gauss map is finite, is generically finite. So there does not exist a variety of general type, subvariety of the Albanese, such that the conormal sheaf of this variety inside AX shows up in the singular support of okay, let me write this down. A composed with tau lower star of CX. Okay. Okay, so we've seen it a few times by now that this I have all these étale maps, and then I can compose them with the abelian Albanese morphism. And if I take this push forward, this is gonna be by decomposition theorem some direct sum of certain perverse sheaves. Then it makes sense to take its singular support, and this is a closed subvariety inside the conormal, the cotangent space of the Albanese. And we know that these all look conical, which means that there exists some closed subvariety inside the abelian variety whose conormal sequence is, conormal space is a component of this, this singular support. So the criteria is that varieties of general type cannot show up if any of this is satisfied. As a component, yes. Yeah. They're all right. Yeah. Yes. So for none of the tau, it can. Okay. Okay, I'll give some examples soon, so these criteria start to make a bit more sense. Okay. Mm-hmm. I think that will be a smaller singular sub. So the set of, if you take union over all tau, that's bigger than taking union over all local rank 1 locals. Okay, so the theorem we proved is that 3 is equivalent to 4. So let me maybe reiterate what it means. A corollary is that, so okay, again, like 1 implies 4 is not very surprising. But let me assume something like, suppose X is a smooth projective variety such that there exists a C infinity fiber bundle structure over the circle. Then, in particular, there does not exist any variety of general type inside the Albanese such that T star Z AX is a component of the push forward of the constant sheaf under the Albanese. So in particular, if the Albanese AX is simple, then having this fiber bundle structure implies that the map, the Albanese map, is cohomologically smooth. And by that I mean that the push forward is a direct sum of local systems. So an abelian variety being simple means there's no sub-abelian variety, which is equivalent to, I mean, in that case, it turns out that any sub-variety of the abelian variety is of general type. So that's why this is quite obvious from that. Okay. Okay, so let me give some examples to see how these criteria manifest. So let's start with an easy example, the abelian variety. So let's assume X is an abelian variety itself. Okay, so let's check one. We know that for all omega, they don't vanish anywhere. So Z omega is empty. This happens for every, I should say, of course. I should have said that everywhere. Okay, so that was easy. The second one, that it's a fiber bundle structure, that's also, we know that A is diffeomorphic to a bunch of copies of S1, where D is the dimension of the abelian variety. So that's also obvious. There are many fiber bundle structure. And then the third one, which says that so I need to show that this is exact. And this is also well known from the theory of generic vanishing. But let's see. Sorry, so A prime for any isogeny. Yeah, so this is a consequence of generic vanishing theory. Also, we know that the Euler characteristic of the abelian variety is 0. So it's not surprising that the alternating sum of this complex is 0. Okay. And then finally, for number 4, so I have to look at the singular support of. So now there's the Albanese, it's itself, its identity. So I just have to look at this. And the singular support, this is a finite étale map. So the push forward is a local system. And it's well known that the singular support of a local system is always the 0 section. yeah, so that's clearly not of general type. Okay. Okay, so that was the case of abelian variety. So now let me give a little bit non-trivial example. So this shows up in the paper of Debar, Jiang, and Lahos, and also Schreider has manifested his criteria for this example. So for this, let C be a genus larger than or equal to 2 curve together with a finite map to an elliptic curve. It's a 2-to-1 finite map onto an elliptic curve. And of course, I called it E2 because there's an E1. E1 tilde is an elliptic curve. Together with an isogeny to another elliptic curve. And this is also 2-to-1. Okay, so then our X will be the following surface. So I take product of C with E1 tilde, and then I mod out by the diagonal action. Okay. So this has a map to C mod, well, let me just write E2. So now I will look at these criteria for X, but I will restrict my forms onto the forms that are coming from E2. Okay, so let's get started. Number 1. P is not, so how does P look like? Let me tell you what the fibers look like. So P inverse of B looks like E1 tilde for B general. Just because we can base change, and they are, if you base change to C, it's a product, and the fibers are E1 tilde, so the general fibers have to be E1 tilde, and the special fibers are kind of, they're not reduced. So in this case, P is not smooth, so for all omega in E2, the 0, I mean, they vanish along the non-reduced fibers. So the 0 set is not empty. So it's kind of opposite extreme of number 1. Okay, so yeah, number 2, I want, let me skip number 2, but let's go to number 3. Yeah. So let's see. Yeah. Yes. Thank you. Yes, I'm restricting to the forms that are coming from E2. Okay, so now I want to say that, okay, so now this gets interesting because if you look at the resonant complex given by so again, P upper star of omega, if you look at it on X, then this is still exact. And this is not, again, this is not an argument, but if we look at the Euler characteristic of X, then that is still 0 because the cohomologies of X are the same as cohomology of the product, E2 times E1 tilde. Yeah, no, E2 times E1. So that's why this has no Euler characteristics, so it's not surprising that this is exact. If you look at now so I'll give you a finite étale cover, and that will justify why we need to take finite étale covers. So here's so this product has a 2-to-1 map onto X, because X is basically quotienting by this degree 2 action. So let me maybe draw the entire fiber diagram. Let me call this tau. Okay, so then this is finite étale. And Euler characteristic of C times E tilde is definitely not 0, because C is a positive genus curve. And this means that if you look at X tilde comma C, and then you wedge it with P upper star tau upper star of omega, then this is not exact. Right? Because this is a complex, the alternate sum cannot be 0, because the Euler characteristic is not 0. Okay, so okay, so this shows that 3 also fails in this situation. Now let me clean. Okay. Oh, I do? Okay, sorry. Yeah, maybe. Okay. Yes. Thank you. Okay. Okay. So then number 4. So now I want to check that this also fails. In other words, I want to show that there exists a variety of general type, which shows up in the singular support. Well, again, the same phenomena happens as in 3, that if you look at this, this map, then the singular support of Rp lower star of the constant sheaf, this is just the 0 section. And that's because if you calculate this push forward, it becomes direct sum of some local systems. So, but on the other hand, if I pre-compose with this finite étale map, then I look at lower star of Cx, the Cx tilde, then okay, so I made the commutative diagram here, and you see that the left vertical arrow is smooth. So if I push forward the constant sheaf there, it's still going to be a local system, but then the map in the bottom is not, it's ramified. So it will definitely see some of the strata, so basically the branch locus. So this will be the 0 section, which is always there, union a bunch of points in E. So P belongs to the branch locus. Okay, so wherever I wrote E, it should be E1. Yeah. Okay, and then the point is P is of general type. Right. The point is of general type. is it? It's yeah, maybe. Okay. Honestly, yeah. I mean, they show up. I mean, so this is a way to. Okay, this here we are. It's a bit hidden actually. So here I'm taking a map to E1, and that's not the Albanese. So the Albanese is E1 times E2, and if I take the map to the Albanese, actually the étale covers are not necessary. So so the étale covers will be necessary for the definitely. In some cases, it will be necessary when we consider the local systems of rank 1. So in order to, if you have a torsion local system, then to make it untorsion, you have to take an étale cover. But beyond that, I don't know if it's actually necessary or not. I don't have evidences. Okay, now I have to erase. I'm very... Yeah. Uh-huh. So in a way, yes, right? It's like about topology of Albanese morphism. So yeah, I guess the Albanese morphism is not very topological, but I see. Yeah, I mean, to me, this was the topology input, and that was the generic vanishing input, and this was kind of complex algebraic geometry input. But okay, you're right. But yes, exactly. I should probably keep it for a little longer. So let me erase this. Okay. Okay, and then finally, I should give one more example. And about this, I can't say anything, but when X is of general type, and it doesn't have to be a subvariety of an abelian variety. In this case, it means that its Kodaira dimension is maximal. Then 1 is known, and this is a result of my bad. 1 is known to fail, so it means that for all one form, we know that there exists some 0. So this is a result of Hoppe and Schnell. And of course, one could ask all the rest of the properties whether they also fail for this in order to check the conjecture or come up with a counterexample. But yeah, I have nothing to say for this, so this is an open question. Okay, so now I would like to show the proof why 3 and 4 are equivalent to each other. But for that, I need some inputs from generic vanishing theory. So this part is probably going to be no news for many of you, but I have to set up a few notations, so I have to review some basics. Okay, so let me write this on an abelian variety, but it should work in general. So let's consider the rank 1 local system, which I will denote by this. So local systems on abelian variety of rank 1. And on the other hand, we have this line bundles of degree 0 times the space of 1 forms. So basically, I want to justify number 3, how the 1 forms come up in the generic vanishing theory. Okay, so here we have local systems. Okay, and then this is a very involved theory of Simpson and Ayn Lazarsfeld and Don Warapura and many other people that these are, well, I'm writing as a set, but also as real manifolds, they are isomorphic. So, yeah, so let me tell you a little bit how this goes. So if I start with a local system of rank 1, then there exists a harmonic bundle, and we saw this in Mochizuki's talk. So this is a line bundle, and it comes with a harmonic 1 form. From that, we can go here to produce a line bundle of degree 0 that corresponds to the 1-0 form given by 0-1 form given by the 0-1 piece of theta plus 0-1 piece of theta bar divided by 2. And then we also get a 1 form, which also one can write in terms of 1-0 piece of theta. Okay? And then people consider some interesting subsets of this. So let me see if I can write it here. So over here, inside of this space of local systems, I can consider the cohomology jump loci given by set of all local systems such that it admits some cohomology. So over abelian variety, this kind of is not interesting, but think any x in place of A. So this is non-zero for some K. And then on the other hand, over here, I can consider Sx, which is given by set of all line bundle, comma, omega, such that, so now a complex that looks very similar to that one will show up. So I'll take the homology of, I'm switched to x, sorry. Then I twist by L, and let's see, I have to put a dot somewhere, and yeah. Okay. This is not exact. Sorry. Okay, so this kind of sets were considered in Arapura's paper, and the most beautiful part of this generic vanishing theory is that these sets are very well. They behave very nicely. So, for instance, on these the generic the cohomology jump loci, they look like finite union of some torsion translates of similar looking cohomology jump loci coming from quotient abelian varieties. So this is a little bit deceiving. I should have written everything for x, and then this will apply on the Albanese of x. But I'll explain in a second why I'm writing this and not for x. Okay. And then on the other hand, we have that Sx looks like similarly peak 0 of b times h0 b omega b1 for all surjection on 2. Okay. Okay, and then similarly, okay, so this is, and this correspondence again goes exactly like the original one. And that tells us that, okay, if I have a local system, I can always associate a one form omega. So I'll consider some similar sets. So now let P be a constructible complex, or bounded constructible complex on the abelian variety. Now I really need a abelian variety. In particular, I can take perverse sheaves. Then consider a similar cohomology jump loci, which now I'll define to be local systems on A, such that if I take the hypercohomology of P twisted by this local system, then this is non-zero for some I. And these sets are also, it's also known that they behave like this, and hence you can associate a space of one forms to them. Technically, we don't even have to go through this. We can take these sets inside the space of local systems. This is an affine variety, and its tangent space is the first cohomology of A. So you can take the 1-0 part of it. That's another way to come up with set of one forms. So this is something we will be interested in. Okay, maybe right here. Okay, so then the way we show the equivalence between 3 and 4 is via proving a statement on abelian variety. So basically, yeah, okay, so maybe before that, I should say that, so if we have a perverse sheaf on, or a constructible sheaf on an abelian variety, then this is one way to get a space of one forms. And another way to get a space of one forms is to consider this singular support of P. This is inside the cotangent space. And the cotangent space of abelian variety looks very simple. It looks like A times H0 because it's a group. So I can just project onto right? So then its image will be inside here. So this is another way to come up with a space of one forms, holomorphic one forms from perverse sheaves on abelian varieties. So then one can ask whether they are equal, and the answer is yes. So RP is equal to pi singular support. So this is the input that goes towards proving the previous theorem. We call this theorem B. So now the claim is theorem B implies theorem A. Okay, so the idea is to apply this on the push forward of the constant sheaf. Okay, so let me show you that. Yeah. Yeah, you could go through the correspondence. But the easiest way to do it is to look at the tangent cones of these subsets, and the tangent cones lies inside the first cohomology, which has a decomposition into 1, 0, and 0, 1 part, and one of the pieces space of one forms. So that's another. They are the same thing. It's not clear, yeah, but no. Right. Yeah. You would need some argument. And of course, there is a parallel picture for complexes of regular holonomic D modules. In that case, we need to consider another space in between the space of local systems and peak 0 times the 1 forms. So those are called the Dirac moduli. So basically line bundles with connections. Okay. So now let me prove the claim. So okay. So let me maybe show that that if there exists a general types of variety, so what? So that would be 3 implies 4. Yeah. X such that P star ZA is contained in the singular support of. So I need to show it for all finite at allomorphism, but for simplicity, let me just assume that it's already contained in the push forward of the constant sheaf. Then I want to show that wait a second. Yeah, then I want to show that for all omega is not exact. Okay, so okay, yeah. So I just apply this. Okay, so then the idea is to apply theorem B for the push forward of Cx. So let's see what this tells us. So this criteria, so by hypothesis, the singular support is everything. So this is because Z is of general type, and that means that the Gauss map is generically finite, and the Gauss map. So that means that this requires a little bit of argument that if you project onto, if you look at all possible conormal vectors that show up here, then it covers, it surjects onto the the space of global one forms. Okay? So this is everything. And then on the other hand, we know that this is equal to RP. And RP is precisely the set of all one forms that come from here. Okay? Sorry, this is a bit. So I want to show that this implies this. So by this hypothesis, since a singular support contains a conormal of a variety of general type, I know that its projection is going to surject onto the space of one forms. And that's, it doesn't use theorem B. So this is theorem B. So actually, this is theorem B. Which means that RP is equal to everything. So it means for all omega, this is not exact. Oh, no, okay, no. So this is a fact about varieties of, so this one is following, it's coming from the fact that since Z is of general type, then is everything. Yeah, so this is a statement. I think this is, at least for smooth subvariety, it's pretty standard, but we couldn't find a proof, so we also include a proof in the paper, but I think this is quite standard. Yes, so this is 4, this is 3. So I only showed one implication. Yeah, the other one is also, I mean, this is basically reversible. That's the idea. Okay, so as we've seen, the main input is theorem B, which is a statement about constructible complexes on abelian varieties. And so, yeah, so so the proof of that, I will assume that P is a perverse sheaf, and then it's an inductive argument from there. Okay. Okay, so I have to show that this one forms that come from generic vanishing theory is the same as the one forms that come from the singular support. And the idea is to go via Euler characteristic. Okay, so case 1, the Euler characteristic of the perverse sheaf is positive, and in this case, it's known from the theory of generic vanishing that RP is in fact everything. So this is because the generic vanishing, the homology jump flow size are basically the entire base of local systems. On the other hand, I want to show that that this singular support is also everything. So for that, we need to use Kashiwara's index theorem. Which says that the Euler characteristic of P is the same as the intersection of all the conormal sheaves that show up in the singular support intersected with the zero sections. Okay, so this Z should be such that the conormal sheaves are singular support of P. Yes, maybe with some multiplicities. Thank you. Thank you. But they're positive. So the idea is that if this is positive, this implies that there exists some Z for which this is positive. And this implies that Z cannot be of general type. Oh, sorry, Z is of general type, my bad. Yeah, and that's what we wanted to show, because then that means that the projection of the conormal sheaf to the space of holomorphic one forms is everything. So we achieve what we wanted. This one from here to here. Yeah. So this is like so this is zero. This is zero when Z is fibered by tori. If you have sub-abelian variety. Yes. Yes. Mm-hmm. Yeah. Thank you. Yes. So this is this. And then it's zero. Yes, exactly. And that's what we will use in the case when the Euler characteristic is zero. So then there's a statement. So this implies there's a statement by Weissauer and also Kramer, Weissauer, and Paresky, Hopa, and Schnell for Hodge module part of the story. And it basically, the idea is, okay, if the Euler characteristic is zero on an abelian variety, then you go to a quotient abelian variety and you can find something that has positive Euler characteristic. So let me write what I just said. There exists an abelian variety such that and a surjection together with a perverse sheaf. So, okay, sorry, I should have assumed the simple perverse sheaf here. Because, okay, so for general perverse sheaf, it's a question one can still ask, and that's actually something I'm working on right now, generalizing some of the results of Paresky, Hopa, and Schnell with Luigi Lombardi. Okay, but for simple perverse sheaf, it is known that there exists a simple perverse sheaf on B such that P can be written as the pullback of this perverse sheaf times some rank 1 local system. Okay. And then the key part is that Euler characteristic of PB is positive. And then we can apply the same thing, and then we have to check carefully that RP is pullback of H0 B omega B1. And the same thing here. So here the Euler characteristic will be 0, hence Z will be fibered by tori, and it will be fibered by exactly the same map. So we get that this is by SSP. Okay, so that shows theorem B. And my time is almost over. So in the last 3 minutes, let me tell you that our original goal was nothing of this sort. We wanted to show that we wanted to show something about the space of holomorphic one-forms that does admit zeros. So let me write something. Let's erase this. So we wanted to study, so maybe let me write original motivation. We wanted to study the space of holomorphic one-forms such that omega does have a zero. And this is really related to this story by what's called Kashiwara's estimate. Which says that this push forward of the constant sheaf under the Albanese map, and if we look at the singular support, and if you look at the space of holomorphic one-forms, they all lie inside W of x. So we really wanted to understand how far these two sets are from each other, and or what's the so now we know that this set is linear. So this looks like finite union of linear subspaces. So the question is Wx linear? Is also a finite union. So that's the question we originally wanted to study. And we ended up showing that two linear subspaces of Wx coming from two different inputs are equal to each other. But however, we did make some progress in this direction, which is basically the following, that if you look at the set of one-forms such that the zero set is really big, in other words, the codimension is less than or equal to 1. Yeah. This may not be pure dimension, but by this I mean that there exists at least one component which has the correct codimension. Then this is linear. By that I mean finite union of linear subspaces. Okay, so that's all I had to share. Thank you for your attention.
Any questions or remarks?
Do you expect in the quasi-projective case the same conjecture with holomorphic forms replaced by logarithmic forms and Albanese replaced by the quasi-Albanese?
So there are some results about zeros of holomorphic one-forms for logarithmic one-forms, but that's for varieties of general type or pairs of general type. But the other ones I would not know how to generalize. Like for instance, like these linearity properties are not known. So a lot of the things are not known. So the correct formulations are, I think, also is not clear what it should be. It's known for the cohomology support loci. The full linearity is known. Okay, I see. Yes, that's right. Yeah, no, okay. Yes, the local system, not the resonant. Okay. Yeah, I see what you mean. Yes. Okay. So then yes. No, I have to think about it. I haven't really considered how to replace, for instance, the fourth criteria, which would be like Albanese morphism, and then it's not really a proper map. You have to somehow compactify it. So yeah, I think there's something to think about that I haven't. Thank you for the question.
Anyone else?
Is it known that when you have a setting like in Euler's theorem, you have a C-infinity map to S1, is it known that X has a holomorphic Euler characteristic equal to 0 already?
That is probably known, but I'm not completely certain. That is probably known. Yeah. Like
it would be kind of a much weaker statement than 2 implies 1.
Yes, that's right.
Yeah.
Thank you. I should have also mentioned that the entire equivalence is known for dimension up to 3. That was shown by Schreider and Fang Hao and Schreider together in 2 different joint work.
Yes, among the one forms you find that that come in the various criteria, can you find some of them which are closed?
These are holomorphic one forms on smooth projective varieties, so they are all closed one forms.
They are okay. So
yes, they are closed one forms. Yes, I think if this was not projective, you have to worry about that.
And when you consider the connection defined by this one form, what happens?
So that's a story that lies in between the local system and the Higgs.
Yeah.
You can consider the same thing, and Christian Schnell has studied holonomic D modules on abelian varieties. And then if you look at these cohomology dump loci, and you can define a similar loci inside the DRAM moduli, and he has shown that they also correspond to each other under this map. So, yeah. So the same story can be stated in terms of D modules, but I wanted to state it in terms of proper sheet.
No one else, then let's thank Yajnaseni again.